In the really old days, people had to write their code directly to work on the hardware. They wrote load and store instructions to get stuff in and out of memory, and they played about with bits and bytes and stuff. You could do pretty good work with that, but it was very specialized. Then they figured out that you could build languages fit for humans for specific areas. Like they built Fortran for engineers and scientists, and they built COBOL for businessmen. And then in the mid-60s, a bunch of Norwegians, mostly Ole Johan Dahl and Christ Nygaard, thought, why can't we get a language that sort of is fit for humans for all domains, not just linear algebra and business? And they built something called Simula. And that's where they introduced the class as the thing you have in the program to represent a concept in your application world. So if you're a mathematician, the matrix will become a class. If you're a businessman, a personnel record might become a class. In telecommunications, a dial buffer might become a class. You can represent just about anything as a class. And they went a little bit further and represented relationships between classes. Any hierarchical relationship could be done as a bunch of classes. So you could say that a fire engine is a kind of a truck, which is a kind of a car, which is a kind of a vehicle, and organize things like that. This became known as object-oriented programming, or also in some variants of it as data abstraction. And my idea was very simple, to take the ideas from Simula for general abstraction for the benefit of sort of humans, representing things so that humans could get it, with low-level stuff, which at that time was the best language for that was C, which was done at Bell Labs by Dennis Ritchie, and take those two ideas and bring them together so that you could do high-level abstraction, but efficiently enough and close enough to the hardware for really demanding computing tasks. And that was where I came in. And so C++ has classes like Simula, but they run as fast as C code, so the combination becomes very useful. Yeah, I say.
So as you can see, so Bjarne Shrewsbury himself, he worked on Simula in his PhD. So there was some object-oriented programming in that, but C++ kind of formalized it. The four main features: abstraction, polymorphism, inheritance, and encapsulation. And one of the most unique things is that C++ is the only OOP language which allows, like, it supports deterministic destructors for its classes. It's not there in any other language in its counterparts. And well, I like other languages just a self-compiled language. So the main two pillars, to sum it up, main two pillars of C++ is the concepts direct abstraction of the hardware features and zero overhead abstraction. So it's lightweight and it's an efficient abstraction, but it allows you to like be connected to the hardware also. So it's just best of both worlds, that's it. And that's why you created it.
Okay, thank you. So she mentioned a word, self-compiled. Have you heard this term before? So in what language is the C++ compiler written? C++. That's what you mean by self-compilation. Okay, so now time for a surprise quiz. +2, -2. Name the two Norwegian. So name the two Norwegian scientists she was mentioning. Okay, just a joke. So no one understood the names, right? What you were saying. So a very quick round of revision now. We saw the base and bounds approach in the previous lecture for relocation. It's a dynamic relocation method. Why is it dynamic? So we discussed few aspects of dynamic relocation in the previous lecture. Anyone wants to have a go?
Can be shifted up and down.
So once a program has been allotted some memory in the physical memory, so you can also change that sometime later during the execution of the program. It's also dynamic because you don't decide it at the compile time. So we have a base register which corresponds to the start of the address in the physical memory. Bounds, which gives us the range. So on what address does the VS start? The virtual addresses starts 0. And at what time are the base and the bounds set? When the process is set up for the first time, or there is a context switch, so then also you might change the base and the bounds during that time. What happens if the virtual address is greater than the bounds? So the program will terminate because of the fault. In terms of the pros of this approach, so the first approach we usually take is the simplest approach. This one is relatively fast. You require only 2 registers. In terms of cons, it needs what kind of memory? Contiguous block of memory leads to internal fragmentation and external fragmentation. So we also discussed segmentation in the previous lecture. The motivation behind using segmentation was to overcome some of the cons of base and bounds. So the biggest cons of base and bounds were that it required a big physical contiguous block of memory, which had to be allocated even in the physical memory. So instead, we said that we have different code. We have different segments: code, heap, stack. We give each of these segments its own pair of base and bound registers. This will lead to somewhat reduction in the internal and external fragmentation. So the total number of registers required is 2 times the number of fragments. Each segment can have what? So that's how it's set up. So each segment can have its own size, its own in some sense start address also. So each segment can also have its own permissions. And so look at the stack and the heap. What's the difference between them? The direction. So each of them can have their direction, permissions, sizes, start address. There are 2 important methods. First is the check. We have to check whether an address is valid or not. So it's a simple check. If the segment start is less than the virtual address is less than segment start plus segment bound. We also have a simple translation formula. It's physical address is given by the virtual address minus segment start plus segment base. Okay, this should not have been pros fast at the end of it. Cons, so while it is somewhat an improvement over the regular base and bounds dynamic relocation, but it still requires a contiguous block of memory for that particular segment. This leads to internal fragmentation, external fragmentation. We looked at some simple examples. Virtual address 0x100 goes to the MMU, goes to the kernel, comes back from the kernel. You have 3 registers, important registers now: virtual address start, base, and bounds. The physical, so the base address plus the bounds is what you get in the physical memory. The virtual address start and bounds is what you get for each segment in the virtual address space.
So in segmentation, how internal fragmentation?
Sorry?
In segmentation, like you mentioned in cons, internal fragmentation.
So you're still allocating a big amount of memory, all of which might not be required.
Like for each segment, like if we're taking for stack,
let's say if I've taken a huge block of memory for stack, let's say I've taken 2 MB, but I'm using only 10 KB. So all of that is unnecessary being wasted. The formula is fairly simple. Segment start less than VLS, segment start plus segment bound. So 100 less than 300 holds true. So this is a valid address. Physical address is given by 100 minus 0 plus 1000 hex. Similarly, 2400. So now this will be from a different segment. If this were from the same segment, we could have returned from the cache. So it returns a different triplet of virtual address start, base, and bounds. This is located physically different part of the memory. It fits into this particular 2000 to 2000 plus 600. That's why it's a valid address. And the actual address on the physical memory will be given by 3000 plus 2400 minus 200. The last case is if the address does not belong to any of the segments. You look at all the segments that you have. The check will fail on all of these segments. So you'll get a segmentation fault. We looked at how to okay, so we were looking at how to get the which segment this belongs to at any given address, plus what's the offset. So we started with which segment each address belongs to. We looked at the fact that we require the top 2 bits in this case because we have 3 different segments. Although we could have also had 4 different segments being addressed by 2 bits. So most significant 2 bits tell us the segment. The remaining bits tell us the offset. So we also have a simple mask with which we AND, and then we shift to get these 2 significant digits. The mask is 1 1, so we basically want to get a 1 1 on the most significant 2 bits. Everything else is immaterial, and then we shift 12 bits to get these 2 as the last 2 bits. So we get 0 0, it's segment equal to code. If we pick up something from the heap, so it has to be between 4 KB and 6 KB. So this particular address is something between 4 KB and 6 KB. You do an AND with the offset mask. You get 0 1 as the most significant 2 bits. You shift.
Why do you need to perform the AND operation?
Yeah, so this question has been asked, like everyone is asking the same question. You could, in this particular example, you could get away with it, but maybe there's a case that there are additional bits to the AND. In this particular case, yeah, you could just do a right shift by 12 to get the same answer. So in this particular case, the segment is a heap segment. Now let's look at the tricky case for the stack. Oh, sorry, for the offset address.
So is that the mask can change from one process to another?
The mask can change from one process to another. No. So until and unless they have. Okay, so let's say if you have processes which line up like this, you can have the same mask if they're using the same address space. But technically the book says that you can use the same mask, but I think there is more to it. So you have to take it with a grain of salt. So in this case, so what's happening is you have this program code in 0 0. Let's say if it was less than 2 KB, and your heap was right next to it. So then you can also technically have the same significant 2 bits for the heap. Make sense? But that doesn't, then the 2 significant bits do not help us to figure out which segment we are using. So these are some of the flaws which have generally not been discussed. But in a practical implementation, I'm sure that this would have been taken care of. Or there would be some assumptions that you at least give this amount of space to each segment, so that you have a shift, you have a change in the most significant 2 bits. Okay, so now let's look at the offset. This is the second part. The offset naturally would be given by the remaining least significant 12 bits. And offset is relatively easy to calculate. It's just virtual address times ANDed with a mask. So the mask is going to be 1s at all of these positions, because we want to do an AND with the number so that we get all the set bits. Let's look at an example. Again, the same address from the program code. You do an AND with 1 1 1 1 1 1 1 1 1 1 1, which is, so this is hex. If you represent this in hex, this is FFF. So you get 1 0 1 0 as the offset into this particular segment. Now let's look at the segment register which we had. So code has a base address of 32K and a size of 2K. This is the bound. Heap has 34K, 2K, stack is 28K and 2K in the physical memory. So an offset of 1 0 1 0 for a code. What physical address will we get for this? So the physical address is given by the base address for that particular segment plus the offset into it. So the base address for code is 32K plus the offset. 32K plus 1010 binary, which is 32 32768 plus 10, and this should be decimal. Let's look at the stack now. So we pick up this address, which is 15k in virtual address. So 16k corresponds 16k in the virtual address space corresponds to 28k in the physical address space. 15k should correspond to so 15k should correspond to
15 into 2 power 10.
no, so let's not look at any complicated mathematics. So which direction is the stack growing in? 28k is the, so 16k corresponds to 28k. 16k minus 1k corresponds to 28k minus 1k, 27k. But is the formula working correct now? So you have, the formula was base of segment plus the offset. Now, if you calculate the offset for this, like you look at the 12 least significant bits, this amounts to 3k. So if you use this simple formula, you have 28k plus 11, this thing in binary, which is 3k, so the address is 31k. Is it right? No, right? So this is not equal to 27k, which follows our intuition. Let's try something again. Maybe so this is someone who's just taking wild guesses who doesn't know anything about the formulation. So maybe, yeah.
So how did we use 3k as the offset?
These two, if you look at these 12 bits. So what is this in binary? What is this in, what is this amounting?
Into some multiple of
This is 3k, right? So that's how we got the offset. So the first two significant bits, which is 1, 1 in this case, tell you that it's from the stack. The least 12 bits is the offset into the stack. So it's 1, 1, 0, 0, 0, 0, 0, 0, which is 3k. Which is, if you use the simple formula, you get 31k, which is not equal to 27k, which you would have expected. Let's maybe change the formula. Do you think this will work? No, right? So someone who's just taking wild guesses might think, we just reverse the order for stack because stack goes in the other direction. So instead of having a plus offset, you have a minus offset. This doesn't work, right? You get 28k minus 3k, which is 25k. So what could we do to get 27k as the answer? So we know the answer. We need to find a way to get this answer.
Plus offset minus 2k.
Offset minus 2k. Why minus 2k? Okay, so one way to get it is to get plus offset minus every stack. The other way, so I generally tend to look at as you just draw the blocks. So you have to somehow get 1k above the base address. So we can actually have the formula which is somewhat simplified, somewhat more generalized, as in the base of the segment plus the offset minus the offset for the first address. So now in all of the cases that we've been seeing thus far, the offset for the first address was 0. Like if you looked anything up here, the offset for the first address was 0, the offset for the first address in the heap was 0. But the offset for the first address in the stack is? No. So the first address has, this is the offset for the first address. And this is 4k minus 1, so for simplicity, let's keep it to 4k. So the basic thing is, the first address has an offset of 4k. If if the offset you found is 3k, so effective offset you found is minus 1k. Make sense? So you have got 1, 1, 0, 0, 0, 0, you subtract out 4k, you get minus 1k. This is 1k, and with the minus sign you get minus 1k. That's why it's 27k. But if the formula seems complicated, just use your intuition and just see that you move 1 byte, 1 KB above in the virtual address space. You need to move 1 kilobyte above in the physical address space. Pretty simple to remember that way. Okay, so thus far we've been seeing that we require the base, the start virtual address for the for each segment, and we require a size or a bounds. But if you want to make it more generalized, or if you want to ensure that we can also include in the stack, which goes in the other direction, so we store another bit, grows positive. That's how. So now there's an additional register required, or you can store it in any other bit in any of the other registers. Okay, so we discussed the example about sharing support yesterday, but let's look at it again. So we have these different segments, and another bit or another set of bits that is stored for each of the segment is the protection features. Whether the code is read, write, execute, is it read, is it only write, and so on and so forth. We would use this across, we would share code across processes in order to save memory. In examples for that, so for the examples for that would be we've got a same code which we run multiple instances of it. The code segment doesn't vary. Everyone with me? Code segment is read only. It's created like it's put in once by the compiler. It doesn't change during the execution of the program. So why have multiple copies of it? So so you place it once. You have a single code segment in the physical memory to which multiple processes can have the virtual address code segment pointing to it. Everyone with me? Okay, so what does the OS have to do for segmentation? In terms of context switch, what does the OS have to do?
Bring in the
So store the current set of segment registers, restore the newer processes segment registers. The OS has to manage free space, which is allocate and deallocate upon creation and termination. And it also has to periodically do some compaction or defragmentation in order to ensure that new processes can still get allocated new memory. Why is segmentation good? So it's compared to, so whenever we're looking at moving to more advanced technologies, let's compare them with respect to the base technologies or the technologies they're improving upon. So compared to base and bounds, is this still fairly simple? You require some additional bits, you require maybe one additional register. It's still fairly simple. It's one of the biggest advantages that for different segments you can have different protection bit set. So you can, this is something else. So this is, in order to check whether the address is correct or not, you just require n comparisons for n segments. In the previous case, you required lesser number of comparisons because you had a single contiguous block. You have multiple contiguous blocks, there is more number of checks required. Translation is a single addition once you found out the correct segment. Still fairly simple. The other big advantage is that, like we saw that in the previous example, if we have the same exact copy of a process running, we don't need to create code segment for the second process. We can just reuse it. And you can also protect regions of memory appropriately for the different segments. And eventually it will lead to lesser internal fragmentation because now you have not given one big block of memory, you have given smaller blocks of memory for the different segments.
So how is that possible? Because in the earlier case, we had, let's say, one of our segments is, let's say, 2K.
Right.
Our all address space was 2K into 4. Still, all address space is 2K into 4 and is still allocated inside our memory. And they are internally having the same internal fragmentation levels. I think the external fragmentation is much better handled.
So in terms of internal fragmentation, let's say so we gave this to the code segment, we gave this to the heap, and we gave this to the stack. So what happens with the space?
Oh.
So this is if you're just using base and bounds.
So we are not considering that it's, we are having different bounds in this segmentation.
Sorry? Yeah, so now we can have different sizes and different bounds for each of these. So now, effectively what's being translated is, this was a different base and bounds, this is base and bounds, and this is a different base and bounds. All of this space is now left free. So.
But it's still limited by that addressing policy, right? The MSB2, the first two MSBs still dictate the size and.
Sorry, I didn't get your question.
So the MSBs dictate the size of the maximum size to which we can allocate, and it's not we are allocating the maximum size. It's still limited by.
So the most significant bits will tell us the number of segments we have, and the least significant bits will be the maximum number of
possibilities, but
yeah.
It's still limited by the bound.
Right.
Okay.
Why is segmentation bad? So it's better than base and bounds, but it still requires the entire segment to be contiguous in memory. Why is this bad? Again, fragmentation. And potential for both external and internal fragmentation, more so for external in this case. So what we did was to move from base and bounds to segmentation. Effectively what we did was to say, why not break it up into smaller chunks, give each of them the base and bounds. So here's a simple thought experiment. We saw that large contiguous memory can cause problems. What if we were to map each byte of the virtual address to a byte of the physical address? So let's go to the total extreme. What happens in this case? So it's a lot of overhead, right? So one of the goals of OS, specifically the memory management, was we want to reduce the overhead of the OS. If we manage each byte, or if we map each byte of the virtual address to a byte of the physical address, so there is a lot of overhead. The OS has to maintain on a per process basis the entire structure. But does it reduce fragmentation? So will there be any fragmentation in such cases? No, right? Because for each byte on the physical address is the corresponding byte on the virtual address. Does it reduce external fragmentation? Yes. Does it reduce internal fragmentation? Yes. The only case it won't be able to reduce internal fragmentation is when the process requires lesser than a byte, and you're still allocating it a byte. So how much space do we need per process? We need a lot of space. So the way I'm trying to lead you is that, so we started with giving the entire process the entire contiguous memory. That was bad. We moved to segmentation, which was somewhat better. We then went to the other extreme, each byte for each byte, which is bad. So can we do something better? So yeah, that's a good idea. So can we go somewhat between segmentation and a byte to a byte? And you've studied this in architecture, so you already know the answer. Paging. Hopefully this video plays.
Okay, let's look at a sample problem. Suppose we're given a computer with...
Does anyone know this movie? No, okay, you know. So those who don't know should try. Okay.
Okay, let's look at a sample problem. Suppose we're given a computer with a 16-bit virtual address and a page size of 256 bytes. The system uses one-level page tables that start at address hex 400. Maybe you want DMA on your 16.
So page tables has been, studied for long. This is a picturization of Harvard, I guess. And I don't know, maybe it was Professor Matt Welch who was teaching the course. Mark Zuckerberg is sitting there, someone is passing him some sheet of paper, which is censored for this class. Okay, so paging is important, it was always important. So the the crux of the idea is to divide the memory into smaller blocks, as some of you have suggested. So let's start with an example. You have 64 bytes address space. Let's say we want to break them into 4 chunks. So each of this chunk is called a page. So how big would each chunk be then? 16 bytes. 16 bytes per page. So let's say this is how our virtual address now looks. You wanted to address 64 bytes. You've broken them into chunks. Similar idea as segmentation, but now it's a uniform chunk that is given. And each of them is called a page. 16 bytes is called a page. But if you're dividing the virtual address, do you divide the physical address space also? Yes, no? Yes? No? Why? Okay, so why do you think we should not? So the idea is you map them into the same physical, like you could technically get away with it because you're providing an abstraction, you could hide away those details from it. But this is one of the efficient ways to do it. Like technically you could break them up into pages, but after that have a layer of segmentation. But we're trying to move away from segmentation. So we give them all the same amount of blocks or pages of same size are given to both the physical memory and the virtual address space. So let's say this is how a particular example, a particular instantiation of the physical address space looks like. There is some amount of pages which are reserved for the OS itself, requires some memory. And let's say this was the address space of the process. And it had 4 different pages. So we're required to address 4 different pages from the process's address space to the physical address space. So in this case, the first page goes to page 3 on the physical address space, so on and so forth. So similar to segmentation, similar to base and bounds, just that now you have a 4K, you have just a 16 bytes unit, which is splitting it up. So it's done. So this mapping between the virtual page or the virtual address space to the physical page or the physical address space, it's by a data structure called page table. So no prizes for guessing a fairly intuitive name. So in the previous example, we saw that the virtual page 0 mapped to the physical frame 3. So we'll have these terms thrown around, frame or frame number or page number. Many of them are used interchangeably, but we just stick to something which is done in the book. I may by mistake say something wrong in the lecture, but stick to the stuff being taught in the book, read in the book. So is this a per process data structure or can I have a single data structure? So again, it has to be a per process because for different processes you'll have a different mapping between the virtual address and the physical address. Everyone with me? Okay, so let's continue with this example. So we have 64 bytes. Let's take 64. The number 64 would require how many bits to represent? 6. 2 raised to power 6 is 64. So we can go from 0, 0, 0, 0 to 1, 1, 1, 1, 1, 1. So the address space which we want to create is something like the following. So we have 4 pages of 16 bytes each. So page 0, 1, 2, 3. Now, how many bits do you require to address to find out the page number? 2, because we have got 4 pages. As we've been seeing thus far, the last 4 bits tell us where in 0 to 16 you are. So where exactly are you in this page? What's the offset to the page? The first 2 bits tell us which page you are in. So again, we keep on using similar set of techniques for all of the methodologies that we've seen thus far. Let's say if there is an instruction which is move 21 to EAX. So 21 would mean in binary would be 010 101. So let's break it up into 2 parts. The last significant, the least significant 4 bits and the most significant 2 bits. Now, do we need to do anything with the 4 bits? So if we want to find out where is this address? So everyone knows this, 21 is a virtual address. Everyone with me? So when we actually need to load something, we need to go to the physical address. So the physical address would need to be computed. It has two parts now because we want to find out which page this lies in. The last 4 bits are the offset into the page. The first bits tell us which page this belongs to. So this is called virtual page number. This is the offset. Now if we go back to the mapping, which we saw previously, 0, 1 or 1, page 1 goes to page 27, if you can't see. So it goes to page 27 in the physical memory. 7 is what in binary? 111. Page 1 goes to page 7. I'll write them again. So 0, 1 is translated to 111. Do we need to translate the offset? No, right? This is again following the similar ideas that we've been seeing thus far. The offset moves as it is, unless and until you're using the V8 case of stack. But otherwise, if moving the address space in a single direction, the offset moves as it is. You only need to translate the first 2 bits, which is find out which page in the so what page number in the virtual address corresponds to what page number in the physical address space. There you have the split. This is the page physical frame number. Page frame number, I don't know I think physical frame number. And this is the offset. So in summary, this is the idea. Fairly simple idea. You have the offset, which you don't care about. Like technically you do care about, but you don't need any mechanism or any hardware to do the translation. And you have the virtual page number. You have an address translation unit, which will give you the corresponding physical address. Simple. Everyone with me? So now let's take the example of storage. So how many bytes do we require per process? Let's do some calculations. Let's consider a 32-bit address space. So we have 4 KB pages. So the page size is 4 KB. Now 4 KB is what in binary? The 2 raised to power? 12. So if we have 4 KB corresponds to 12, so we have got 12 bits offset. Everyone with me that this corresponds to the offset. And how many remaining bits do we have? 32 minus 12, which is 20. So we have 20 bits left. What is the number of pages? Which is, sorry? 2 raised to power 20 is, so it's a huge number. Let's just keep it at that. 20 bit pages, which is to the power 20 pages. Now, how many address translations what's the worst case number of address translations that we will require? Let's go back. So for 2 bits, what is the number of translations maximum number of translations that we could require? For 20 bits, to the power 20. It's a huge number of address translations required. So this is clearly not a very optimum design, but that's what we have. That's what we have. And let's say that we require 4 bytes per translation. So what we now require is 4 into 2 raised to power 20 megabytes, which is 4 MB per process. Is it?
Number of translations per number of pages.
So maximum number of possible translations that you can do. So maximum number of addresses, maximum number of pages you can see is the maximum number of translations, unique translations. Put it more succinctly. So if you give 4 bytes to the data structure, which will help you to do the translation, you'll require to the power 20 into 4, which is 4 megabytes per process. Is it a big number? Big number, small number? So people have been doing address translations since the time we didn't have this much amount of RAM or this much amount of this much amount of even onboard storage. How many of us have used floppy disks? Okay, Bob, like what was the size? No, not the physical, like the storage size. Does anyone remember? No, it was not in KB. Right?
Physical size or like
Storage size.
1.44 MB.
1.44 MB, right? This is 4 MB. So in fact, like I've also used floppies, but I've not used floppies as people have used before me. So Windows used to be shipped in floppies. So you would get a stack of floppies, and you would keep on installing. You would like, keep on replacing floppies one at a time. Okay, so let's play around with these numbers. So previously we had a 4 KB page size. Let's move to 8 KB page size. Now what changes? The number of bits required is, previously we required 12 bits. 13 an additional bit is required. 13 bit is the offset size. The remaining bits are 19, so the number of pages is 19, which is the maximum number of page numbers, virtual page numbers you can get. Number of translations required is also reduced. So now you require 2 MB per process. Let's keep on moving in this direction. 5.2 KB pages now. So we started with 4 KB, now we move to 5.2 KB. 19. So I used to, like, I was working these out and many times I forgot the calculation. I was storing this in my mind. 13 bits remaining, which is 13-bit VPN, number of pages to the power 13, translation is to the power 13. So it's a small number now. So what we've arrived to as so we've arrived at page size trade-offs. If we have a small size, we require a lot high number of translations. So that's bad. Which is also corresponding to a lot of overhead per process. So we saw 4 MB per process when we were using 4 KB page size. But the good side is that there is a very less chance of fragmentation. Can anyone explain why fragmentation is less probable when you have small size?
Yes,
And why is that?
you might not need all of the space.
So let's say you have a
Because stacking.
sorry,
Better stacking.
better stacking.
Like you can place memories.
So let's take an example. You require 9 bytes, and you have page size of 1 byte. Is anything wasted? Is any space wasted? No. You require 9 bytes, and you give a page size of 4 bytes. How much space is wasted? 3 bytes. If it's 16, if the page size is 16 bytes, you're wasting 7 bytes. If it's 32 bytes, you're wasting 23 bytes. So that's the idea. If you have a really small page size, you're very less likely to have fragmentation because you're giving you've broken it up into smaller pieces, and each of that chunk can be used to fill up the whole. But if you have a large size, as we saw, so we'll have lesser number of translations required, which is good in some sense, which also means that there is a lesser overhead per process, but it's bad because now the chances of internal fragmentation increase, which will eventually lead to external fragmentation at some point. Okay, so I don't like when animations go out of place. Okay, again, don't look at that. So where is the page table stored? It's not really stored on the MMU. So it's actually stored in memory. So let's look at this particular example. This page table says 3752. Anyone wants to take a guess what 3752 means?
One is virtual, the ordering of the virtual.
So the first bit here corresponds to, let's say this is an array, 1:1 mapping. So this stores the location on the physical frame where the 0th virtual address is stored, or where the 0th virtual page is stored. 0th virtual page is on physical frame 3. First virtual page is on physical page frame 7, so on and so forth. So we require a very simple data structure. In this case, it's just a simple array, which contains so this is called linear page table. And in future lectures, we'll see that why this is linear and why this is not optimum. Could we do something about it? So 3 to 3, the second bit 7, third bit 5, and the fourth one 2. So let's look at the remaining part of this video.
Assume page table entries have 8 status bits. The 8 status bits would then be, anybody? I see we have our first surrender. Don't worry, Mr. Zuckerberg. Brighter men than you have tried and failed with this class.
1 valid bit, 1 modified bit, 1 reference bit, 5 permission bits.
That is correct. Does everybody see how we got there?
So what else is in the page table? Zuckerberg gave the answer, but so we have protection bit, as in for each of the page, is it readable, writable, executable, or what? Present bit is the page currently in the memory, or is it in the HDD or SSD? What scenario do you think this would be useful? Yeah, he knows it. Swapping. But if you don't know swapping, what, in simple terms, what scenario do you think could be used? So let's say I want to load Adobe Illustrator on Raspberry Pi. So how do you think the execution will go on? Like, do I use all the features of Adobe Illustrator at a single point of time? So most of the stuff resides on the memory, on the hard disk. Only when I require to access a particular filter does it come to the memory. So can we have something on that lines? So we don't require to load everything into the memory. That's why there's the present bit, whether it's in memory or it's in HDD or SSD. The reference bit. So is the page which is being referenced, is it referenced often enough or not? So for every page we have an entry, is the page popular or not? And what happens with unpopular pages? So they will become, from present they'll become absent. So they'll be swapped out to the HDD SSD. We have a valid bit, whether the translation is valid or not. And there's a dirty bit which says that has this page been modified or not since it's been brought to the memory. So many of these things you might have again studied in the architecture course when you're talking about caches and cache coherency and things like that. So we'll just now very quickly see what's coming up in the next lecture. Caches, like we've been discussing cache a lot. We'll be looking at something called as translation leukocyte buffer, which you might have again studied in the architecture course. We'll look at OS memory management, like what kind of data structures does the OS need to maintain in order to free the memory or in order to look at which page to allocate the first physical page available. And so we looked at this data structure which was a linear page table. Can we do something better? So we looked at 2 raised to power 20 entries would be required, and then such simple linear tables. Can we optimize it? So one such idea, just to leave you with an idea, would be that we create a page table for a page table, so which reminds us of recursion in some sense. With this, I'll end the lecture today.